Good morning. Good morning. So, all of you are doing well?
Yes, sir.
Great. All right. So, once again, you have to see this face for the next few weeks. All right. So, let me see how many of you are here around today. 25. Let me check once. Shubham, are you there?
Yes, sir.
Moitrio,
Present, sir.
Ashif,
Present, sir.
Nitan,
Present, sir.
Shitama,
Present, sir.
Elanjan,
Present, sir.
Shabul,
Present, sir.
Girish, Girish is not there. Shukanna,
Present, sir.
Shanton,
Present, sir.
Debago, Orkojyoti,
Yes, sir.
Konad,
Present, sir.
Pritam, Medha,
Present, sir.
Arnav, Chasti,
Present, sir.
Vrishti,
Present, sir.
Suchishmita,
Present, sir.
Shruti,
Present, sir.
Anuraj,
Present, sir.
Pranav.
Yes, sir, I'm present.
All right. Shomili,
Present, sir.
Shaurin, Shaurin, Akash,
Present, sir.
Mandaj, Aditya,
Present, sir.
Anirban, Shurujit,
Present, sir.
Protoy, one, two, three, four, five, six. Okay. How many of your friends have already left after first year? Any idea?
So Somutra has left.
Yeah, that I know officially. Anybody else unofficially?
No, sir.
No. So the others are not there. Didn't bother. Okay. All right. So before we start, because as Professor Chakraborty has already mentioned about that the mid-semester part will be covered from the topics that he has already covered. I'm just, I'll just start either from today or from tomorrow. But my part, whatever I will cover before mid-semester, will not be there in your exam. Have you received any communication regarding mid-semester, when mid-semester is going to start?
22.
Yes,
So
sir.
that
From 22nd
Or this
November.
has already been notified, right?
Yes, sir.
Yes, sir.
Okay, good, fine, very nice. So yeah, so only the organic chemistry part that Professor Chakraborty has covered, that will be in your mid-semester examination. So for the next few classes until mid-semester, I'll continue. And after mid-semester, Professor Chakraborty, when he will return back, he will take the number of classes that I will cover, and then I'll continue through the end of the semester. Fine, very good. So let me
Sir, I wanted to know one thing. When mid semester is on 22, but when is our end sem means tentative dates?
That's already there in the academic calendar, right?
Okay, it's okay, sir.
Yeah. I think 22nd is also in the academic calendar, I guess.
Yes, sir.
Yes, sir.
Yeah. So the institute is trying to trying to now stick to the academic calendar, because otherwise things will get delayed, and already it's in a mess, and slowly we are trying to clear that mess.
So
So I
it's
hope,
17th January, something like that.
yeah, I think sometime in the end of January, right?
It's the 17th to 24th,
Yeah.
I think.
Right. So if it is 17th, so before that, 1 week there will be a study leave. So that means until the semester will continue through January 10 or so. And yeah, so we have good time before that. All right. So before I think when your end semester is going to end, do you have any idea? Have you already received your end semester, sorry, mid semester schedule?
No, sir.
No, sir.
No. So as per calendar, it would be on 29th, right?
Yes, sir.
Okay. So you will soon receive email from my office about campus return from December. So after mid semester, we initially thought of calling you back in the middle of this month, but then we realized that you have a mid semester examination, and then shifting and moving might create a little bit of inconvenience. So therefore, and also it requires certain renovation in the hostels and all, so which are now being taken up. So maybe after mid semester, from the beginning of December, you will be called to the campus. Particularly, all the laboratory classes will resume in offline mode. Theory classes also, depending on the instructor, if he is in the campus, I think you can attend physically. In my course, after mid semester, all of you can attend in person in my classroom. So be prepared for that. But before that, don't think right now about the campus return, because you have mid semester only about 10 days to go. It's already today is 10th November. Okay, so let us get into business. Before we start, I don't know where to start, because I need to take a stock, and that's why I thought of where to set the stage for this course. Because the first semester, I don't know how much topics have been covered, particularly the inorganic chemistry component. So let me ask you that definitely your bonding, atomic structure, and the molecular structure part, the bonding component, how much has been covered? Any one of you, maybe I'll ask Akash. Are you there around, Akash?
Yes, sir.
Yeah, Akash, can you tell me what topics of inorganic chemistry have been covered in semester one? Because semester two you had no inorganic chemistry. So can you just tell me?
Sir, in semester one, there was only physical chemistry, sir. No inorganic chemistry in semester one.
Yeah, I see. That was primarily a general chemistry component. So the atomic structure part
Yes, sir.
was
There are
covered.
some sir did some molecular orbital theory, some
Yeah,
and their diagrams like some O2, H2,
correct.
carbon monoxide. Some of them was there, and some orbital picture drawing.
Yes.
This thing was there.
Okay, so the atomic orbitals and other things in a semi-quantitative or maybe qualitative way, you learn that why these orbitals, why the atomic orbitals look like that. All these things definitely Professor Devshankar Rai has covered, right?
So, and that part on ionic lattice, that Madelung constant, and that part was briefly covered.
That part was not covered.
Like briefly covered.
That was briefly covered. So what about the molecular structure part, particularly the different models of structure of compounds, like the inorganic compounds, where you primarily need to learn the Lewis model? I think all of you have studied those at your BSc level, at your 10 plus 2 level, like the Lewis model and then valence shell electron repulsion model. and then the molecular orbital model. So normally one should learn that way, the way it progress. So the Vishpar model you have, all of you are comfortable with.
Yes, sir.
Yes, sir.
Okay, so there is no problem with the Vishpar model, right? Because when I progress, I will definitely take stock whether whether you are quite comfortable with the structure of the different inorganic compounds, particularly that contains the lone pair electrons, and whether that lone pair electrons, how it affects the geometry of the molecules, and eventually what is the shape of different molecules, depending on the number of lone pair, how it affects. So basically, most of the basic structural parts have been covered, but the in details that the one component, particularly the solid state, has not been covered. Right? That's what my feeling is. Is that correct?
Yes, sir.
Okay. All right. So yeah, that we'll talk about. So and then question comes about the acid-base chemistry of the ionic equilibria, particularly the acid-base equilibria. In your first semester, you had the laboratory course on acid-base equilibria, and there I think you have covered the basic acid-base equilibria part, particularly for the Bronsted acids. Definitely, the Lewis acid part has not been covered, so that I'll take up. And redox part I covered a little bit in your AEC course in the last semester, but I will go a little deep into that, because that's most important part of inorganic chemistry, to understand the reactivity of inorganic compounds. And then I'll go to the little bit of main group chemistry and transition metal chemistry. So that's the course structure that is there in this semester. And so let me take you to what I would like to cover. And to start with today, I think I thought of giving you a kind of brief overview of the topics, and what exactly we are going to learn in this course. All right. So is this visible?
Yes, sir.
Yeah. So as you can see from this slide, that in this particular course, where we would focus on the structure and reactivity of inorganic compounds, and these inorganic compounds means the compounds of main group elements, the compounds of transition metals, particularly the coordination compounds. But this will be a very general and an overview of the subject that will cover the basic fundamental concepts of the reactivity and the properties of different inorganic compounds. And as a result, we would like to take up topics one after another, from acid-base chemistry to redox chemistry, and then to transition metal chemistry and main group chemistry. But primarily, we will base on redox chemistry, because I told you also in the previous semester that if you learn redox chemistry, learning main group chemistry is very easy. So we should focus only on the acid-base chemistry and redox chemistry much in details, and then yes, few classes that I will cover on coordination chemistry and transition metal chemistry. All right. So as if you just look at in a briefly that how we should think of understanding structure, properties, and eventually the reactivity of compounds. We start from atoms, they form molecules through the affinity of atoms to others, and as a result, they form chemical bond. The molecules have unique structure depending on the constituents of the molecule. So what are the different atoms present there, how they form the chemical bond, and what is the electronic structure of the molecule that determine the structure. And every structure has symmetry because the molecular symmetry is an important aspect in understanding that property of different molecules. So this symmetry component of molecule, because symmetry is an integral part of, of understanding the molecular properties as well as the bonding in compounds. So the symmetry, I will not go in details into it, but I will touch upon that what the symmetry means in molecular system and what information we can get by understanding symmetry in molecules. So when we talk about structure, because the structure that you can draw on a paper, you can make use of different models to see the three-dimensional orientation of atoms, and then you get a picture about the molecule. And when we know that how they bind with each other, that the constituent atoms bind with each other, then we can get information about their molecular properties. And these molecular properties, say, for example, whether a compound will be a redox active, that means whether it will participate in electron transfer, or whether a particular compound will behave as an acid or it will behave as a base. For that, understanding of the structure is important. Understanding of bonding is important. And quite often, different bonding models like Lewis model or Vesper model, they do not give definite answer. These models are not adequate to understand the properties of these molecules. So eventually, we need to know the molecular orbitals, picture of those compounds. And for understanding molecular orbital in a more quantitative way, there is something called group theory that you will learn at a later stage, where the mathematical aspect of symmetry in molecules will help you in developing molecular orbitals of easy to even very complicated molecules. And then you know whether a particular compound will be a reducing agent or an oxidizing agent, or it will act as a Lewis acid or base, or whether it will interact with other molecules or not. That will help you in understanding the molecular properties. And these molecular properties, can be obtained from different, can be probed. So once you know that, yes, this is my molecule, but what are their properties? So they are bonding properties. That means in a molecule, when different atoms combine, exactly at what distance different atoms are oriented, what structure it is giving. These in the bond parameters in the three-dimensional geometry, these are actually giving a lot of information, and this can be probed by different spectroscopic techniques. And you had some information about those spectroscopic techniques, very basic. You will learn those things in details. So when we talk about the molecular properties, like every time when we talk about acid-base property, when we talk about redox properties of a molecule, or when we talk about whether a system, what is the geometry of that molecule, we only consider a, our unique or an isolated molecule. But in this material world, when we talk about inorganic compounds, when we talk about any compounds, not only inorganic compounds, but any compounds, it's in bulk, right? Whatever we see in this material world around us, these materials are made of molecules, either in pure form or in mixture, but they are bulk. So not a single molecules are present there. You have multiple, or actually several molecules are present there. And the presence of so many molecules together would dictate their properties. So how many molecules combine with each other and eventually coming together, and the interactions among molecules, either similar type of molecules or different type of molecules in bulk, how they dictate the properties. That there comes the molecular interactions. That means the interaction beyond molecule. So what is that interaction beyond molecule? The interaction beyond molecule means that it is more like outside the domain of molecule, because when we talk about molecule in an isolated molecule, for example, we talk about bonding. We talk about whether it's an ionic bonding, whether it's a covalent bonding. There is nothing purely ionic or pure covalent. There is always a kind of certain percentage of ionic bonding present in covalent system or covalent in ionic system. That depends on the properties, something like the electronegativity of atoms in molecules or the electron affinity of the atoms in molecules. But electronegativity is a parameter that involves the atomic property in a molecule, because electronegativity is nothing to do with an isolated atom. So these properties eventually give rise to the bulk properties of the molecule, and that bulk property can be understood that how they stuck together and giving rise to unique properties, just like very simple water molecule, right? If you look at it and try to find out what this water molecule is. So you have one oxygen atom, two hydrogen atoms, they combine, and then you know that oxygen is more electronegative than hydrogen, and you know the Lewis structure of that. So, but Lewis structure will not tell you how it looks like, what is its three-dimensional disposition of three atoms in space. So for there, what you need to know that, okay, how many unpaired electrons are there? Lewis model tell you that yes, there are two lone pair electrons on oxygen, and Wishpur models tell you that because of the repulsion between the two lone pairs on oxygen, which decreases, which pushes the bond pair, and as a result, the hydrogen angle that decreases from 109.828 degree to 105 degree. Now, yes, you can probe by spectroscopic techniques that indeed the HOH angle is 105 degree. You can find out from spectroscopic techniques what is the OH bond distances, and also you get information that water behaves, that it has two lone pair electron. Fine. If it is a two lone pair electron, the question is, are the two lone pair electrons same, or They are different. That's the one question. The second question is, does the structure of water tells you anything about what would be the nature of water in bulk? It doesn't. So the bulk water is liquid. If you freeze it, the volume increases, density decreases, and you see the nature's creation of this molecule in a unique way, that this water, when it freezes, it floats on water. So the ice floats on water has implications for the survival of aquatic species, particularly in cold region. Because even if you have ice on top, you have water at the bottom. But this property of water, the bulk property of water, what is the factor, or what are the different factors that makes the properties like that? Different molecular interactions that we should know, that why the bulk properties of water are like that. These type of interactions are called non-covalent interactions. So in water molecule or in any other molecules, the information you get from the molecular properties and you go to the bulk properties, for that you need to know how one molecule interacts with other. So if one molecule interacts with other by some sort of interactions, there could be many different type of interactions. And we should know what are those interactions. And these interactions are called intermolecular interactions. And they are definitely much weaker interactions compared to the ionic or direct bonding covalent interactions between the atoms. Yet, these weak interactions play a pivotal role in dictating the bulk properties of molecules, which eventually dictate their reactivity with other compounds. So this is what, in a nutshell, we should think of the way we should look at the molecules, their properties, and eventually the reactivity of those molecules in bulk phase. Okay, so now I'll go to these non-covalent interactions. Okay, so these different forces, the chemical forces or weak intermolecular forces, we should know that what these chemical forces are and how these chemical forces bring together atoms, ions, or molecules. The atoms and ions we know already, that how they form bonds, how they form ionic bond or covalent bond in molecules, and then they form the structure and eventually the molecular properties. But when we talk about bulk property, as I mentioned, and as I repeat again, that how molecules can come close together. So when you take a solid or in solution also, think about a sodium chloride, the salt that you take at home, or any other compounds in their solid state. You don't have one molecule present there. You have so many molecules present there. How they stick together? There are different forces, and these forces are dictated by different properties, like when we talk about ionic radii, when we talk about chemical bonding. You have seen that, okay, ionic radii in an ionic system, ionic radii of constituent atoms, like in sodium chloride, you would like to see that, okay, I would check what is the ionic radii of sodium ion and what is the ionic radii of chloride ion. So when they form bond, when sodium chloride is formed, the Coulombic interactions, and also not only the Coulombic interaction, but repulsion of the electrons, of the core electrons of the constituent atoms in that molecule, they bring together the two atoms to an optimum distance. And this optimum distance, where the energy is minimized, that defines the distance, and this ionic distance in such is actually considered to be the bond distance, where you just take the sum of the ionic distances. Whereas for covalent bonding system, when we talk about, let's say, carbon-carbon bond, or carbon-fluorine bond, or fluorine-fluorine bond, we then take the covalent radii. And this covalent radii, if you have an identical atoms like carbon-carbon, right? And you know that carbon-carbon distance, how do you get it? The carbon-carbon distance in a single bond is about 1.54 angstrom. Now, what is the covalent radii of carbon then? It is considered to be the half of the distance of the, since these are two identical atoms joined together. So the covalent radii here in this case would be approximately the radius of the core electrons and half of the distance of the identical atoms. So the carbon-carbon distance, if you take it, divided it by 2, and you get a covalent radii of carbon. Similarly, in fluorine molecule, so you see here that for the carbon-carbon bond, the covalent radii is considered to be 77 picometer or 0.77 angstrom. If you take two fluorine together and the fluorine-fluorine bond distance, you can get this from different spectroscopic tools, exactly what is the fluorine-fluorine distance in a compound where primarily covalent interactions bring the two fluorines together, form bonds, and then you get a distance of about 142 picometer. So the covalent radii of fluorine here would be about 71 picometer. Now this is about an identical atoms when they form bond. But assume now, what would be the CF bond distance then? If you know this, can you find out what would be the CF bond distance? Will the CF bond distance be the just sum of these two, the covalent radii of carbon and covalent radii of fluorine? No, because now here there is a problem. These two atoms do not have the same electronegativity. Now we are talking about these bonding interactions in a molecule. So as a result, the difference in electronegativity between carbon and fluorine will make the carbon and fluorine bond different, and the distance will not be sum of the covalent radii of carbon and fluorine, because fluorine will try to pull the electron density towards itself because of higher electronegativity. So if I just check from the spectroscopic techniques, any spectroscopic techniques, there are many different spectroscopic tools by which you can get an information about the bond distance, like infrared spectroscopy. It can tell you how strong the bond is, but definitely it will not tell you exactly what the bond distance is. X-ray diffraction technique is one technique which can tell you what the bond distance is, exact bond distance is. That is means you take a solid and you pass X-ray, and then you take the X-ray diffraction pattern, analyze the pattern, and from there you get an electron density map, and from the electron density map you get the information about the bond distance. Now, in molecules where you have carbon and fluorine bonded together, it is observed that the CF bond distance is about 1.36 angstrom. Now, if I just consider the covalent radii of carbon and fluorine and just sum them up, one would expect this should be 148 picometer, but the actual distance is 136 picometer. So far, we are talking about the distance in molecule. But there are different models that try to explain that how theoretically we can predict and try to match with the CF bond distances that are observed experimentally. So one such model, or in fact all the models, they considered that this difference in electronegativity will take care of the reduction of the bond distances compared to the sum of the covalent radii of the constituent atoms. So, as I said, in most average carbon-fluorine bond is about 1.36 angstrom or 136 picometer. So Mulliken, who worked a lot on electronegativity, and I will talk about electronegativity a little more, maybe tomorrow or sometime, that how you really get information that electronegativity is not something which is always fixed in a molecule. And there is something called electronegativity equalization. But that apart from that, different models were developed, and all these models, and I always say this, let me tell you once again, that models are always good. The models are like, putting brick on foundation. That means it will increase the knowledge base, and one would try to find out whether the model is appropriate to explain the experimental data or not. Not all models can explain all the experimental results, or a single model cannot take care of the experimental results. But as long as a model takes care of certain experimental result, that means yet it can explain a certain experimental result, then it's worth working with. Because this way, the model comes, and then there will be another model which will be a better model than that, and then another model will come, and this way you basically improve the model. And at some point, you will find that a model is developed which can take care of most of the experimental results and can explain almost everything, and there that model is well accepted. But none of the models that you just can throw away, right? I mean, there are so many different type of bonding models are there, but do we really throw them all away? No, we work with hybridization model, but hybridization model miserably fails in many inorganic complexes, many inorganic compounds. So hybridization model is a one model, like Lewis model. Lewis model is a model that tells you that, okay, here you see the octet fulfillment of atoms in the molecules, and it can provide you information that this compound will have lone pair electron, and here so many bonds will be present there, and you get resonance structure, whether some bond will be a single bond, some bond will be double bond. This resonance concept you can just work with based on simple Lewis model. But Lewis model does not tell you the properties of the molecule in details, number one. Number two, it cannot tell you about the about the geometry of the molecules, right? And the shape of the molecule. And then you have a Vesper model. Vesper model can explain many things, but Vesper model also does not explain many other things. For example, you can draw a Lewis model, and then on the basis of that, you can go to the Vesper model. And a simple molecule like oxygen or even water. Oxygen is paramagnetic. Vesper model, neither Vesper model nor Lewis model can explain the properties of oxygen, that why it is paramagnetic. And for that, you need to go to the molecular orbital theory. And now here you see I altered model and theory. Why I call it a theory? Because so much of iteration on these different models eventually tell you something which is more acceptable and which can explain almost every experimental results, that then it is established as a theory. So as long as these models are working, you can work with that. It can lead you to somewhere, and then effectively this works. So along in the same line, like water. You know that, yes, water shape will be like this. Geometry is tetrahedral. The shape is like an angular one. And because of the lone pair repulsion, it can tell you, yes, there are two lone pair electrons. You can say, okay, because of the lone pair electrons, water autoionizes and it can form H3O+. But it cannot tell whether the water molecule will or the lone pair electrons, the two lone pair electrons on water molecules, whether they are same or whether they are different. We assume that they are same, but actually it is not. And that is the reason why water has so unique properties. So the lone pair electron, let me tell you right now, I'll tell you, when we talk about a little more about the bonding in molecules, then I'll show you that water, the lone pair electrons on water are not same. So one is a true lone pair and another one has bonding character. And because of that, water molecule can form hydrogen bonding interactions with another water molecule, but one lone pair acts as a hydrogen atom acceptor and another hydrogen atom interacts with another water molecule where hydrogen atom is donated. So water molecule is called a hydrogen atom acceptor and hydrogen atom donor. And that is responsible for the non-covalent interactions called hydrogen bonding interactions. And these hydrogen bonding interactions in a particular orientation give a geometry of water molecules in solid state, which provides a structure in the solid state that has a hollow structure. And as a result of that hollow structure, the volume increases and it becomes low and density. So this is applicable for many other systems. And here, the one I wanted to tell you is about the structure, the bond distances, the model, which takes care of the electronegativity difference. And now here you see that one model takes care of that, yes, the sum of the covalent radii has to be adjusted with the difference in electronegativity of the constituent atoms. So one such is that so when you work with a model, in front of you, you have a large number of data, experimental data. And then you try to see which model, or you come up with a model and then you see whether they are fitting or not. And then if it is a reasonably working model, then you put forward it that, okay, this can now be utilized to understand what is happening in the system. So this model, where it takes care of that, the sum of the covalent radii between carbon and fluorine, and adjusted by the difference in electronegativity, which is delta X of carbon and fluorine being more electronegative. So it's like electronegativity of fluorine is about 4, whether the electronegativity in Mulliken scale, and the electronegativity of carbon is 2.5. Now, if you take that difference and using this model, you try to get the information about the distance between carbon and fluorine. This turns out to be 134. There is another model which not only considers the difference in electronegativity, but it considers the difference in electronegativity square. And this difference in electronegativity square multiply with 7, adjusted with the ionic radii, the covalent radii of carbon and fluorine, and this gives you a value of 132 picometer. And both of them are actually close to the experimental value of 136 picometer. Okay, the first one in this case is better fit with the experimental result than the second one. So this tells you that electronegativity plays an important role within the molecule, the bonding, and also the electron distribution within the molecule. Now, when you talk about these chemical forces, the covalent bonding, you will have a different kind of bond polarity, and you get an information about the nature of the interactions. But when you go to the bulk scale, this already, let's say the CF bond, right? That we have seen just now. So in a molecule, if you have a CF bond, this already has reorganized the electron density from within the carbon-fluorine nuclei towards more on the fluorine, because the electron density on fluorine is now getting higher. And this pulling of the electron density towards itself will continue until the electronegativity of fluorine and carbon with a certain partial charge on them becomes equal. So what does it mean? It does mean that as the fluorine is more electronegative, it pulls the electron. So you have a delta negative charge on fluorine. And now the carbon will have a delta positive charge. Now the electronegativity is a concept, is the power of pulling the electron density from within the internuclear distance or internuclear region towards a particular atom, and its power is called the electronegativity. Fine? But that is in its inherent electronegativity. So if I assume that carbon and fluorine, initially no charge was there on the top of carbon or fluorine. So there is an electronegativity difference. But as fluorine develops a little amount of electronegativity on it, carbon becomes delta positive charge. The electronegativity difference goes down. So the electronegativity of fluorine in its neutral form is more than the carbon, but as the charge develops on fluorine, its electronegativity is more or less going towards closer to the carbon when carbon develops some amount of positive charge. So this will eventually go to a point where it will, it will develop some charge on each one of them, either on carbon or fluorine, and that charge, it will continue until that partial charge develops on it. So the electronegativity get equalized, and this equalization will make the bond perfectly, or it is in a position where it will get an optimum bond distances. So as a result, this negative charge or positive charge on constituent atoms as a result of electronegativity difference of those constituent atoms in the molecule, the partial charge that develops will make the bond polar. Once a polar bond is formed on a molecule, this will try to interact with another polar molecule from the opposite end. So it is precisely the same concept when an ionic molecule you put in the lattice or solid in a bulk phase, there will be an interaction with the polar molecule to another polar molecule, and then they just form the cluster or lattice or whatever it is. That is the reason why if you take a polar molecule and if you try to dissolve in a polar solvent, you will have an interactions. That means you have a dipole is already there in your molecule, and you already have a solvent which also has a kind of a dipole. If the polarity of your molecule is more, or if your compound, the constituent molecules in the compound is more, then it will induce polarity in the solvent. And this way, they will arrange just by Coulombic interactions, and these polar molecules and the charged molecules will interact with each other. So there will be a polar-polar interactions. There will be a polar and relatively less polar molecule, but this polar molecule can induce polarity on the other molecule. So you can have an ion-dipole interactions, or you can have a dipole-dipole interactions, or you can have a dipole and an induced dipole interactions. So this type of interaction, so dipole-dipole interaction is like when you have a polar liquid, you can have these interactions. You can have the solid lattice, you can have similar interactions. So this type of forces, the chemical forces that bring together different molecules close and in their different form, either in the solid state or in solution, that in fact brings them in the bulk phase, and that structure as a result, such kind of structures that are created due to those interactions will dictate what would be the bulk property side. So as I said, there is another one called induced dipole. And this induced dipole is if your molecule is polar, and if you bring in a non-polar species, but non-polar species can be polarized, if possible, polarized by your polar system. So the polarization of the electrons of the non-polar species or the constituent atoms in the non-polar species will bring together through and chemical forces called induced dipole. So you have purely ionic interactions, but that ionic interactions is in the molecular system. Then you can have a Coulombic interactions between the ions and a dipole, or ion. So ion and dipole, a good example, sodium chloride. When you dissolve it in water, what happens? sodium chloride dissolves and sodium chloride is solvated by water. Sodium ion is surrounded by water molecules. And chloride anion is solvated by water molecule. Not only water molecules, where sodium chloride is soluble. And this solubility will depend on how your solvent and the ion is interacting. And here it is an ion, and the dipole of water molecules is in fact interacting, right? Because oxygen being more electronegative in water, it has a delta negative charge. Sodium is Na plus. And why sodium chloride lattice is broken? Because sodium chloride lattice energy should be, overcome by the amount of energy that is released due to the hydration. So this is called a hydration of ions. So sodium ion will get hydrated, and as a result, sodium and chloride anion will go apart. And this hydration energy makes the sodium chloride soluble in water. So this is an ion and dipole interactions. Now, if you have a polar molecule, and if you try to dissolve that polar molecule into an aqueous solution, it is not an ionic molecule. Let's say it's a covalent molecule. But that covalent molecule will dissolve it in a polar solvent, provided you have these dipole-dipole interactions. So your molecule has a dipole, and the solvent has a dipole, and these dipole-dipole interactions will make the molecule dissolved. Similarly, the other interactions, dipole and induced dipole, right? If you have a molecule which has a dipole, but in a solvent which is not, there is no dipole in it. But what it can do, the electron density in that molecule can be redistributed or can be forced. So this is called induced. One can induce some amount of charge on it. Or sometime you can make a instantaneous dipole creation. So I'll get into the instantaneous dipole creation a little later, but now talk about the solubility of, let's say, some organic molecules in water. We know that most of the non-polar organic compounds or even polar organic compounds are also not soluble in water. But you know that alcohol is soluble in water. You also know that many different sugars or organic compounds from natural sources like carbohydrates, proteins, they are soluble in water. Here, this solubility depends on that what are the interactions that are already present in the molecule and whether that interactions, and as a result of these interactions in the lattice of that molecule in the solid state, can be broken. Those interactions can be broken by new interactions that will form in the solvent. So water is a polar solvent. Alcohol is a polar solvent. You can have dipole-dipole interactions. In addition, as I mentioned already, that water has a unique properties of forming hydrogen bonding interactions. So some compounds which can form hydrogen bonding with water, they also can form, they can be made soluble in and in those solvents. So you have so many different type of interactions. Say, for example, look at it now. You are all very familiar with, you might have seen there, the liquid nitrogen or liquid helium, right? You might have seen at ISCS, or even if you have not seen it, you can see it anytime. And liquid nitrogen and liquid helium, they are used as a kind of a low temperature cryogenic purposes. So this, how you in fact liquefy it. In order to liquefy it, you need to bring the molecules close together because they are gaseous molecules. Helium is basically they are noble gases, completely, the electron shells are paired off and everything. There is no dipole moment. And then how do you, in fact, liquefy it or even sometimes solidify it? It is something like what you do. You, in fact, create a pressure. And that's basically the role of the liquefier. The liquefier, what you have is called something called compression, right? So you compress the gas, being close together, forcefully. But still you cannot make it. But sudden compression will make, let's say, one layer of molecule and it forcefully created a dipole, an instantaneous dipole. So if you have an instantaneous dipole here, then it will create a dipole and it will induce it with the other molecules. So the moment an imbalance is created on the electron density on these non-polar atoms or molecule and causes a momentary polarization of the electron density, it will now induce this polarization to the neighboring atoms or neighboring molecules. And that means they will now be close together. And because of this close togetherness, you are actually forming this gaseous molecule to a liquid state. This is true for nitrogen. Is that you are doing the same thing. Nitrogen is related, there is no dipole there. But what you are doing, you are creating an asymmetry in the electron density just by a sudden electron density imbalance by putting an instantaneous pressure. So this is called that instantaneous dipole, and then that dipole induces the dipole on the neighboring molecule, and this brings it in the liquid state. This is sometimes called the London dispersion forces as well. These forces, as I will show you after some time, they're actually very weak forces. But as you will see, that how these weak forces will play important role in dictating the properties in their bulk phase.
So this momentary disturbance in electron density is this can be induced by electric fields.
Yes. So hydrogen bonding interaction is another such weak interaction. Non-covalent interaction, intermolecular interaction, not within the molecule, no intramolecular, but these are intermolecular interactions. So hydrogen bond is created when a hydrogen atom is bound to a very electronegative atom. Like the most electronegative atoms is fluorine. And then you have also the oxygen, nitrogen, chlorine, they are electronegative atoms. So when a hydrogen is bound to these electronegative atoms in a molecule, they will try to form hydrogen bonding interactions. And these hydrogen bonding interactions will, in fact, form a kind of a dipole-dipole or ion-dipole kind of interactions. And they influences the properties of the bulk of a molecule in the bulk state, and they create, they influences the properties. They influence the melting point, boiling point, density, and many other parameters. So this is something like this. So if you have an electronegative atom and hydrogen is bound to that, that means hydrogen has a delta plus character because it has already been polarized. And this now delta plus can interact with another negatively charged ions, and so that they can form this kind of weak interactions. And these weak interactions are very strong sometimes. So we call these are weak interactions, but they are sometimes very strong if highly electronegative atoms like fluorine binds this hydrogen in a linear fashion. So it all depends on the strength of the hydrogen bond varies. The hydrogen bond will be very strong when this FHF, this angle is linear, that means 180 degree. If it is angular, if it is less than 180 degree, then the hydrogen bonding strength decreases. And then after some, depending on what are the atoms, right? Whether the atoms is not fluorine, but it is a chlorine, or it may be something like nitrogen. Then depending on these two atoms, the electronegative atoms, the angle also changes, and the angle, the less the angle is from 180 degree, the hydrogen bonding becomes weak. Yet sometimes they play a role in dictating the supramolecular structure. Supra means beyond molecule, right? These are something what we are talking about are the supramolecular interactions. So here, if you just see that if you have a linear and symmetric like HF, if you take an hydrofluoric acid, the hydrofluoric acid never stays in HF. It always ionizes, autoionizes, and forms HF2 minus and H plus. So this is because the hydrogen is exactly stays in the middle of the two fluorines, and it stabilizes this anion, HF2 negative anion, so much that the species that dominate in HCF solution is this one. Hydrogen bonding also plays a role in the hydrates of different compounds. Hydrogen bonding is important. I think all of you know. I don't need to really teach you this part. When we learn a biology, the double helix structure of DNA, the protein structure, like the secondary structure of protein, tertiary structure of protein, or quaternary structure of proteins, you have hydrogen bonding interaction both in the alpha helical geometry or conformation of protein or beta sheet conformation of protein. Their hydrogen bonding is important. There are so much control of these weak interactions on the reactivity, on the structure, not only in biological system, but also in solution phase chemistry outside biological systems, and play important role in dictating the properties of the compounds. Just simple example of water of hydration. We call sometimes some molecules, we call, okay, these are hydrates, because if the solid state contains water molecules. Sometimes we say that, oh, this is absorbing water. So hydration in the solid state, when it contains water molecule in the lattice, their hydrogen bonding stabilizes the lattice structure. For example, you are all familiar with the copper sulfate structure. The copper sulfate you have seen, that's blue in color, the solid state. But if you heat the copper sulfate, slowly, you'll see the color of the copper sulfate changes. And eventually, when all water molecules, because in copper sulfate lattice, per copper center, you have 5 water molecules. And if you have these 5 water molecules around it, it creates an environment that is, and the bonds, which creates an electronic state between the different levels where the electrons reside. That makes it blue in color. But as the water molecules are removed, you basically get an anhydrous white solid. And that can easily be proved by doing analysis just by you take copper sulfate, you heat copper sulfate, and you can have a ramp of heating. And so the temperature gradient, you can keep on increasing the temperature with time. And you see that with increasing temperature, the mass loss is taking place. So 64% mass loss takes place until 390 degree. Before that, there is mass loss here. At 215 degree, there is a mass loss. 71, that means you have a mass loss of approximately 25%. And then at 330 degree, there is a little mass loss of about 7%. And then at 390 degree, there is no change. So if you just calculate that how much water is being lost, so at 71% indicates, mass loss indicates, you can calculate that molecular weight and then amount of water. So 100%, considering the molecular weight 100% and loss of 1 water molecule, what is the percentage of the mass? Loss of 2, loss of 3, and loss of 4 water molecules represent about 71% of the mass. So 29% loss equivalent, 29% of this molecule is equivalent to 4 water molecules in terms of molecular weight. And so 4 water molecules you see is lost at 215 degrees Celsius. But after that, the last water molecules, the 5th water molecules requires very high temperature, which tells you that not all 5 water molecules are similar. They have different roles. So the look at the structure that the 5th water molecules in fact binds with the copper center. And that's why it's a stronger bond. And it's difficult to remove at low temperature. Whereas the 4 water molecules are present in the lattice. Okay, I understand that you need 65 degree, you need 100 degree more, at least 100 degree to remove water. No, it's in the lattice. So you have to overcome the lattice energy to break the copper sulfate. And then only you may think of removing the water molecule. But you in fact need 215 degrees Celsius. The reason is the 5th water molecule that is coordinated with copper is in hydrogen bonding interaction with the rest 4 water molecules. And to overcome this hydrogen bonding, bonded water molecules, you need a high temperature. And that is the reason why it gives you an information about the structure of copper sulfate in the solid state structure. So if you just look at that how hydrogen bonding plays a role, let me tell you how liquid water looks like. In the bulk, it's a randomly oriented hydrogen bond forms because there is a dynamics always. And because of the dynamics, hydrogen bond forms, hydrogen bond breaks, and this keeps on moving, going. Okay, so once this hydrogen bond is broken, this can form hydrogen bond with this. Because if it moves there, it loses, it becomes far away from this. And as a result, they can form hydrogen bonding interaction with different molecules at different times, which is nothing but it's called dynamics. Whereas in the solid state, you see they are very ordered. And because of the ordered structure, this hydrogen bonding interaction, this one interacting with this one, and this hydrogen here, the small hydrogen is interacting with the oxygen. whereas this one is interacting. This hydrogen will interact with another water molecule, and this way it forms three-dimensional lattice. And this three-dimensional lattice has a void space inside, and this void space is in fact responsible for the increase in volume and low density. There are different kind of structures of water that are possible. One might think of that, how do we know that what is the structure of water? How do how did you do any diffraction studies on ice, how that can be done? In fact, the ice structure can be obtained in different solid matrices, right? That if you have water,
Sir, you're not audible. Sure, okay.